Okay, so we're going to have a look at a nice property of even and odd functions. So you've got an even function if it maps from the reals to the reals, and then whenever you put in minus x into your function, you get the same output as if you'd put x into your function. So when we draw a graph of an even function, you get a nice line of symmetry in the y-axis. And an odd function, if you put minus x into your function, then instead of getting the same output, you get the negative of the output you would get if you'd put x into your function. So this gives us, for all of our positive points, you've got a corresponding negative point. This gives us a nice rotational symmetry about the origin. So we can have a look at some simple examples. So f of x is x squared. You can see this is going to be even. So if you put in minus x, you get the same output as if you put in x. But then something like x cubed, you can see is going to be an odd function. So you'll spot here even power for an even function, and we've got an odd power for an odd function. And there's no reason we can't generalise this to having sums. So let's say you've got f of x is x to the power of 4 plus x to the power of 8. You can check that this is an even function. And we could go further and actually have linear combinations as well. So let's say we've got 4x cubed minus 8x to the 7. You can check that this is going to be an odd function. And as well as generalising to sums, we could actually have an infinite sum. So let's say now we've got f of x is, we'll call it the sum from k equals 0 to infinity of ak times x to the power of 2k. So this gives us x to the power of 0, x to the power of 2, all our even powers. You can check that this is going to be an even function, at least where this converges. And we can write something similar for an odd function as well. So we've got the sum from k equals 0 to infinity of, we'll call it now bk, times x to the 2k plus 1. So this gives us x to the power of 1, x to the power of 3, x to the power of 5, and so on. You can check that this is an odd function. So what we've got here is actually we've got two sufficient conditions for having an even or an odd function. So if it's made up of only even powers of x, you get an even function. If you're made up only of odd powers of x, you get an odd function. So what we're going to be interested in is the other half of this. So are these sufficient conditions also necessary for having an even or an odd function? So it's not immediately obvious that you couldn't perhaps have some sort of clever infinite combination of even and odd powers and get out an even function. Of course, there are going to be some examples that don't quite fit into this framework. So for example, if you've got f of x is equal to the modulus of x, because this function isn't differentiable, it doesn't have a nice Taylor series expansion, and unfortunately for this, we can't write it as a polynomial or as an infinite sum of powers like this. So these functions which don't have a series expansion aren't going to fit into the framework. So we're just going to restrict ourselves to functions which are infinitely differentiable, in fact. We could generalise this a little bit further by looking at Laurent series if you're interested with negative powers, but we won't go into that today. So now let's just take a moment to digest exactly what we're going to prove. So we've added some assumptions here. We need our function to be infinitely differentiable at 0. So when you differentiate, you get the second derivative, the third derivative. All of these derivatives are well defined at 0. And we also need the Taylor series to actually converge to our function in some neighbourhood of 0. Then we can apply these results. An even function must only contain even powers in its Taylor series, and an odd function only contains odd powers in this Taylor series expanded at 0. And this will apply in a neighbourhood of 0. It won't necessarily apply for the whole function, just because it might be defined piecewise and you might have some quite weird behaviour away from 0. And we need this fact that the Taylor series actually converges to the function in a neighbourhood just to avoid some really quite nasty examples of functions which can't be well described by a Taylor series. We've also got three lemmas here, which are all quite basic properties of odd and even functions. We'll prove these all at the end. They're quite simple to prove. But basically we're saying if you've got an odd function at 0, that function's always going to be equal to 0. This will be really useful. And then these two lemmas, these are really useful as well. So the derivative of an even function is an odd function, and the derivative of an odd function is an even function. So if we get started, we'll assume that f is even, satisfying our assumption. So if we let f be even, then we consider its Taylor series expansion at 0, so its Maclaurin series expansion. It's going to be f of 0 plus f dash of 0 times x, plus the second derivative at 0 times x squared over 2 factorial, and so on. And we can write this much more concisely as a sum, so we'll write it as the sum from n equals 0 to infinity, the nth derivative evaluated at 0 times x to the n divided by n factorial. So the strategy to show that we only need even powers is basically we're going to show that the coefficient of all of our odd powers of n is 0. So this means we're going to show that all of our odd order derivatives are equal to 0. So what we can do now is we can start applying our lemmas. So we know that f is even, so this tells us, if we apply lemma 2, the derivative of an even function is odd, so this tells us that f dash is odd. Then applying lemma 3 to this function, the derivative of the first derivative gives us an even function, so the second derivative is now even. And we continue like this forever, alternating between odd and even functions. And this is really useful now because if we look at all of the odd functions, we can apply lemma 1 to these, can't we? So f dash of 0, because f dash is an odd function, this is going to be equal to 0. Similarly, for the third derivative, evaluated at 0, this is going to be 0. Similarly, for the fifth derivative at 0, and so on for all of our odd order derivatives. So we've shown that all of our odd order derivatives are going to be 0. So then we can conclude that f of x, when we write this using our Taylor series expansion, if I change the index now from k equals 0 to infinity, all of our odd powers of x have a coefficient of 0, so we can just write this as the 2kth derivative multiplied by x to the 2k, all divided by 2k, all factorial. So we've shown then that an even function in its Taylor series expansion, at least in some neighbourhood of 0, is only going to contain even powers. Now the proof's very similar for an odd function. We consider the Taylor series again, and what we're going to do now is try and show that all of your even powers of x have a coefficient that's 0. So if we apply our lemmas once again, we know that f is odd, so the derivative of this is going to be even, the second derivative is going to be odd, and so on. So this tells us now, if we apply lemma 1, the fact that an odd function evaluated at 0 is 0, this tells us that f of 0 is equal to 0. We also know that the second derivative at 0 is equal to 0, and the same for the fourth derivative, sixth derivative, and so on. All of our even order derivatives are now equal to 0. So just like before, we can then conclude that f of x, when we write this using our Taylor series expansion at 0, we can get rid of all of our even powers of x. So we'll now write this, changing the index again, k equals 0 to infinity of the 2k plus 1th derivative evaluated at 0 times x to the 2k plus 1, all divided by 2k plus 1 factorial. So this is saying now that when we've got an odd function satisfying our assumptions, we only need odd powers in this Taylor series expansion. So now all that's left to do is just prove our remaining 3 lemmas, and these are all really simple to prove. If we start off, we want to show that an odd function is 0 at 0, so let's consider what happens to f of 0 for an odd function. You know that 0 is equal to negative 0. Then we can use the definition of an odd function, so f of minus 0, because it's an odd function, has to be equal to minus f of 0. And this is where we see that f of 0 has to be equal to 0, because f of 0 is equal to the negative of itself. So that's only possible when f of 0 is equal to 0. So we've proven lemma 1 there. For lemma 2, if we start off with an even function, we need to show that the derivative of this is going to be odd. So this is again very simple. If you start with the identity f of minus x is equal to f of x, this is true for all x, then differentiate both sides. By the chain rule, we get minus f dash minus x is equal to f dash of x. But then if we multiply by minus 1 on both sides, we end up with f dash minus x is now equal to minus f dash of x, which is the very definition of having an odd function. So we've shown that the derivative of an even function is odd. Finally, to prove lemma 3, if we start off with the definition of an odd function, so we know that f of minus x is equal to minus f of x for all x, then differentiate this identity on both sides. Again, using the chain rule, we get minus f dash of minus x is now equal to minus f dash of x. Then, getting rid of the negatives on both sides, we see that f dash of minus x is equal to f dash of x. And this is telling us that the derivative function f dash satisfies the definition of an even function.